Okay, good morning everyone. I hope you're all well and energetic for the second day of IFL. As you can see outside, the weather is beautiful, and I hope it will stay like that for the rest of the day. So by now a good tradition to have an invited speaker at IFL, and of course this year's instance continues this nice tradition. We drew up a long list of names which we wanted for the invited speaker. On top of the list was Fritz Henglein, who would be willing to give the invited talk. He immediately said yes, so I was very pleased with that. I think Fritz is probably very well known to the functional programming community. He says his research interests are in the semantic, logical, and algorithmic aspects of programming languages, which probably translates into he's interested in everything that has to do with programming languages. And quite interestingly, his interest spans sort of both type theory and sort of algorithms and data structures, and more or less coincides also with my interest, because for that reason I was very keen to have him as the invited speaker. I think he's probably best known for his work on type inference and the presence of polymorphic recursion. If you're a Haskell guy, you probably have toyed with this addition to the Haskell compiler, a little bit polymorphic recursion. And I just told you that this one of his most cited papers, type inference with polymorphic recursion, from 1993. But I told you I noticed we're getting a bit old now. He's also quite famous for founding a company that was fighting the year 2000 K-bug, again using techniques from type inference. And today he's speaking about sorting. So probably you may think that there won't be any surprises more for sorting. So I'll probably assume that you're all trained in computer science and you know sorting is an n-log n algorithm. And I think Fritz will tell us a little bit about how to do better than that. Okay, over to Fritz.
Thank you very much. Thanks, I'm really excited to be here. This is really close to my heart, and you know, as John Donnell already said, that actually, you know, there's some lower bounds, and today I'll show you how to beat them. So this is actually great, exciting work. So you're absolutely welcome to cite some of my more recent work. So you know, don't keep back. It is at the intersection, actually, and actually at the trade-off intersection. I'll come actually into this one, where actually algorithms and hacking meets, you know, the other class of people. I mean, the other class of people is like the ones that say it's all bits, and let's hack the hell out of them, and maybe, you know, support that class in politics, and let's go off in that direction. And there's the other class that says, oh, bits, they're just rather, of course, parts might be English accent there, but of like information, and then we need to have like high-level things, and let's go to, you know, category theoretic treatment, and maybe some time extension will help us, and let's get rid of syntax at all. So actually, there's trade-offs involved. So let's look at an example. Given a list of pointers, how many unique elements does it contain? Please solve that problem. So there's a couple of more variations of this problem. So you might want to think about it. One of them is like given a list of pointers, enumerate its unique elements. Clearly, once you can do this one efficiently, you can also do that one. So variations on that. What if these are not lists of pointers, but lists of pointer lists? So please enumerate its unique pointer lists. Okay, so repeated pointer lists should be not reported. And given a list of pointer sets, well, they're presented as a data structure, maybe as lists that might have repeated elements in them, but they're considered equal modular permutations and duplicates. So then please do the same thing, enumerate its unique pointer sets. So how would you do that? Let's look at a couple of standard solutions, okay? So the first question you can ask yourself is like, A, how efficient are your solutions? And then once you have that in mind, maybe that's the first question you're thinking of. If that's the first question you're thinking of, then you can ask yourself, do you allow copy and coverage collection? Your solutions. Or if you're thinking actually indirectly about this one first, efficient is your solution. Okay. let's look at the first one. Great speed, no abstraction. So this is basically a thing that is like the Java and C solution. Easy thing, what is a pointer? I didn't even say that. A pointer is just something you can convert it to a machine integer, okay? So for example, an address in a machine, like in a RAM. So let's do that. By casting in C or by hashing in Java, Java comes with this built-in thing like poo, and we'll come back to why they have that. A hash code is built into every object. So use address arithmetic and some table lookups. You can figure that one out. It's actually not quite trivial because these tables can be too big. If you use just a little bit, so you might use hashing or whatever, various kinds of things. You might even look at search trees if you want to. Okay. This one will haunt you probably. The pointer set problem is the puzzle with whatever you do. Okay, but let's keep that away. Actually, I'll keep it away throughout the talk and refer to it later. So, consequences of the solution. Potentially non-deterministic program behavior. Actually, everybody who really knows this knows that. If you have a pointer that's a newly allocated pointer, and the memory system is usually treated as a non-deterministic resource. So you get a pointer, and if it's really modeled by a machine address, you get a non-deterministic machine address. And then, you know, with this operation available, convert pointers to numbers, you can do things like if the pointer is less than 4,000, then do one thing and do another thing instead. So you get not only non-deterministic behavior, you can get some very clever attacks on the memory system. No data abstraction. So we've not abstracted the notion of pointer at all. It's just a number that we use to index a linear array called the memory in the machine. So we cannot change the implementation. So think of it as an abstract data type, but you know, by that operation, we basically fixed the implementation. So in particular, try them out in C. People do that. They do it because it's an interesting problem now. It impedes garbage collection. Okay? And actually, impedes actually also in Java. Think about that. What having a hash code means for garbage collection. So that also makes it an interesting exercise, or a job to write a garbage collector for Java because it has these hash codes. So, okay. So we have very powerful operations and a low-level implementation of pointers. Great speed, but we can't change the implementation later on, and some other operations become very, very hard. So let's look at the ML solution. We'll look at an abstract data type called references. And they're systematically restricted to have only quality testing, lookup, assignment, and update. So allocation, I should say, and update functions. Okay. What's the great thing about that? I won't even write it down. Is that deterministic semantics. There's no way of observing in any context of a new, in this case called a ref, whether you've gotten 4000 or 4008 as the machine address. Great abstraction. The only operation you have on references is pairwise equality. That's the only thing you can observe. What about performance? Bad news. Okay, so we use pairwise comparisons to solve our problem. Okay. Pointer-set problem may still puzzle you also here. But there is a nasty consequence. This is actually a sharpening of a lower bound result in sorting. Namely, if you only have pairwise equalities and inequalities, not less than equal, then the lower bound on the first problem that I showed you in ML is n squared. You can't do it efficiently without abstract data reference. So, boy, can't we do better? Well, can you sort and partition? Basically, you've seen this was a partitioning application. Partition just means like you take a thing and then you group the elements according to some equivalence relation. Usually it's the identity, but it could be another equivalence relation. And if you think of sorting actually also as a grouping of the equivalent elements, and then order, writing the partitioning blocks down in the right order, right, respecting the order, then you can see they're basically related problems, okay? Basically variations of partitioning, right? So can you sort and partition generically? That means for many different orders of equivalence relations. In other words, I'll tell you, here's an algorithm that you can use for sorting partitioning, and then it will say, and then people say, well, according to what order does it sort? Well, I don't know, you specify it. Okay, it's generic. But you specify the equivalence relation, partitions. That is fully abstract, which means that, intuitively, I'll have a full definition later on. It means that the result of doing this operation of sorting and partitioning only depends on the pairwise relation between the inputs. That means for sorting, two different inputs that have the pairwise in the input, pairwise same less than equal relations amongst all possible A-squared pairs, right, gives the same result. Okay. So this is a way of guaranteeing that that algorithm that you've used does not disclose anything else than the pairwise order, the less than equal order. Now for the partitioning, that's even tougher, you might say. The result should be the same, and I'll come back to what the same means, but intuitively you should see that it should basically give the same information, or it should not divulge more information than the pairwise equivalences and inequivalences. So if you get two different inputs, and they happen to have in the same position, here that's equivalent, and the corresponding position also equivalent, here inequivalent, also inequivalent, and that holds all the way through, then the result should be the same. A way of saying, like, if you have a set height, you have an abstract data type, only equality on it, an abstract data type, this operation then will not divulge information about the internals of implementing the data, okay? We like to have that. And remember this as well. Okay, so, and it runs in worst case linear time. Okay? With very short and simple program code. Okay? Now, the answer to that question is yes. I'll show you how. Okay? So how do we do that? So let's look at the sorting and partitioning like problems. So it's just rearranging elements according to total pre-order. That's not so unimportant to talk about pre-order. Pre-order means that it's not antisymmetric. When you think about it, when we sort records according to a key, then we sort the records. But you have a total order only on the keys. Now that induces a total pre-order on the records, in the sense that two records could be equivalent without being equal. Okay? That's all it means. So the antisymmetry of total orders is not inherently not interesting. We don't want that in sorting. So partitioning is the grouping of elements according to an equivalence relation. Okay? Often sorting is used as an auxiliary method for partitioning. So, for example, in sort merge join, or when you want to partition something and you happen to have a convenient total pre-order or total order, you can say, "Boy, am I lucky! That data type is equipped with a total pre-order." Oh boy, but you better not give me pointers then, right? But if I have such a thing, then I could say, oh, then I can sort them relatively fast, because with comparison-based sorting, comparison-based sorting is by definition one that is fully abstract, because the only operations it has are its. Okay? So I can use that, and then I have it in the right order, and all you need to do is like the runs, right, of equivalent elements, and then I use that. That's even the case for cases where you are really not interested in the order. You're only interested in the partition. As I mentioned, sort merge join would be a classic one for implementing equijoins in databases. All right, but sorting has its own application. So, all right. So what kind of problems do we have? Well, there is a lot of different variations. The generic structure of sorting partitioning depends on the following. It's like there's many types of elements we want to sort and partition. There's characters and integers and booleans. There's references and pointers. There's structured values, products, records, sums, variants. There's recursive finite, or let's say with the limited ones. There's lists, trees, and graphs as elements you would like to sort or partition. And there's abstract data types. You if you have sets of the rings, or patient records, or file descriptors, you want to also partition those according to usually an identity or an equivalence relation. So many order and equivalence relations on each type. So these are different types of things. But for each type, we have many different orderings we are interested in. So we have ascending, descending order, a trivial order. It's just like everything's equivalent. You know, it's a total pre-order, like everything's equivalent. Case insensitive, only taking the first 4 characters into account of strings. Even, uneven, so sorting numbers according to their even what do you call it, parity, okay? Or partitioning, and the number of prime factors they could have. You know, there's all kinds of things you might sort things according to. Structural equivalence, so which means I can go down into the structure, or equivalence modular order of elements. So like think of it as like we have lists, we've seen it before, and we want to actually think of them as equivalent if one is a permutation of the other. So a list then as a representation of a multiset. So if you use list representations, the equivalence that I've just mentioned, permutation equivalence, gives us equality when interpreted as finite characters. And then written without duplicates, that would give us set equality. Term identity, term equivalence, associative commutative operators, there's all kinds of equivalence relations we might be interested in on the same type of elements. So, let's look at some examples, and I'll give you some examples of how I can solve. This is a DSL, you might say, domain-specific language, for specifying, that's the core of it, for specifying equivalence relations and ordering relations. So, word accords, you know, how many words occur in the text and how often and where, okay? So find all the equal words. Anagram classes could be all the words that are anagrams of each other. Joining relations, database query, term equality with associative, commutative, idempotent operators, and data coalescing of semi-structured data would be an application. So you have a tree thing, and you basically do like garbage collection in a value language, and then you might like to compress the memory requirements by storing a tree only once, so you get a DAG. Pickling, same kind of story, and so on and on and on. So there's many applications of partitioning and sorting. So the general problem is now the following. So we're in need very often of having to do something like partitioning and sorted partitioning. So how do we specify the desired order or equivalence correctly and ambiguously? Okay. So that you always have an order and equivalence designated. How do we go from the order to a correct sorting or partitioning, not only algorithm, but code, okay, that furthermore has a guaranteed optimal asymptotic performance, better can't be done asymptotically, and it guarantees full abstraction. And how to package all this as a toolkit for use in future sorting partitioning-like applications, which is making it generic. Okay. So, once new types and orders and equivalences are defined, the existing code up there can be used for solving problems. Now, our solution is generic discrimination, and a key component is an expressive domain-specific language for expressions for defining orders and equivalences. Compositional approach. So the simple insight is the following one: is if you specify the equivalence relation on some elements by giving a black box function that takes 2 arguments and returns true or false, namely equivalent or no, not equivalent, then we have the lower bound of O n squared, omega n squared. Sorry. Okay. If you correspondingly give a less than equal operation as a black box function that returns a Boolean if and only if one is less than equal to the other one, then we have a corresponding, that's the one you usually know, O of n log n, omega n log n, lower bound, and number of comparisons required to sort. So that can't be the way we want to do that. We need to specify an order or equivalence relation. But actually, these ways are actually dangerous because you could give a black box function usually without, fancy type systems like independent types, without that actually do not implement an inequivalence test or equivalence test, or do not implement a comparison function because they might not be transitive. Just actually, if you want to find out what our algorithm is used in a sorting algorithm, you just stick a comparison function that is not transitive in all instances, because that one will have different behavior on the different algorithms. But all the other stable algorithms will always give the same result if you're given. So there's a possibility of making a mistake when we specify things by black box functions as a way of specifying the orders, and they make them inherently slow. So, but they're very expressive, of course. Anything can be specified. So what we do is instead we define inherently efficient, usually in a time way of doing this by a discriminator function or discriminator functions. And I'll explain what that exactly means by structural recursion on these domain-specific language expressions, okay, on these constructions. So, so then with the discriminator as a central library routine, you can think of it. You can define all kinds of other useful standard routines like sort, class, standard partitioning, sort partitioning, sorting, joining, and so on. Okay, so examples how what this looks like. Okay, so we'll have a generic sorting discriminator called sdisk. It's generic in the sense that the first argument it requires is a specification of an ordering relation. Okay, that's a term. Now here I didn't define it, but there is one that you might say is built in. That means like it's the ordering relation. It denotes the ordering relation on strings of 8 character bits, of 8-bit characters. Okay. So then the word occurrences alphabetically sorted in some text. Here's the words, and here's the index where they occur. Let's just sdisk apply to, well, treat all the strings. Here's the identity of the ordering relation on strings. This is lexicographic ordering relation on strings. And for in order of occurrence in the input, so you intentionally don't want to have a lexicographic order. The words, or actually the indexes where they occur. Well, we'll just use the equivalence discriminator. I'll show you later. Okay. And we need an equivalence expression. So there's more variations of this. So, for example, if you want to have alphabetic order of an input string, of an input text consisting of words, but case insensitive. So you want to identify words that are equal modulo the case they're put in. Then I'll walk you through this one. It means that I first define the ordering on strings that I need. The ordering on strings I need is one that says that it's lexicographic, but modulo the case of the characters, okay? It doesn't play a role. So one way of specifying it, there's many ways. One way is say, oh, let's take the character ordering, the standard. This is for characters. The character ordering, the canonical, Latin one, character ordering, okay? That one induces a character ordering on all characters that is defined by first taking a character, applying 2 upper to it, and also the other character applying 2 upper to it, and then comparing it under that order, okay? That means the original characters, so capital A then would be less than or equal to lowercase b, okay, under that order. Then we say, okay, now we have a new character ordering. Then let's define the lexicographic extension. That's what list L does. Lexicographic extension of any given elemental ordering. Okay. So that then defines the ordering, and I'll just have to apply it to sdisk and we'll do the same thing as before. Okay. And here, similar for if you want to have an order, an occurrence order, not in lexicographic order. Okay, so here's a page you don't have to want to look at, but the thing I want to show you is that down here it says type isomorphism, modular associativity and commutativity can be solved, which means like given a list of type expressions containing one operator, binary operator that is associative and commutative. Think of it as product. Okay? So we want to find out in a list of types, so type expressions, so these are finite. We want to find out which ones are actually equivalent but not only identical, structurally equal, but equivalent under the associativity and commutativity of that one operator, which is the product operator. Okay. So this setup basically means that all I do is I define an equivalence relation. Again, it's like the transformation is applied to the input. Transformation is one that takes the terms and it turns them into a list format, and then applies it to this prod 3 equivalence. And the prod 3 equivalence is just an isomorphism. It basically says that if it's a pair, then it's, you check that, it has the same type constructor, and otherwise, it has to be equivalent under prod 2. And the third part here means that there's a list, it says baggy, so if the two lists are permutations of each other, so the two lists would be of products, like it would be like not just a binary product, it would be an n-ary product. If one is a permutation of the other, then I consider them equivalent. So that's what I'm supposed to. So basically, that solves the problem. And by master theorem, it solves in linear time. Actually, this was a result published separately in mid-90s. It was discovered actually rather late that this can be solved in linear time. This is the complete. You might say this is a constructive solution. And furthermore, you can just stick it in and run it. At least before the most recent version of Haskell came out. For some reason, broke. I don't know. I got some type error that like this big, so I don't know. So orders. I mentioned total pre-orders, reflexive, transitive, and total. It's not necessarily antisymmetric. So let's look at order constructions, and the order constructions give us actually language we need. So a trivial order on any type, that's an order, which means everything's related to everything. Standard total orders and primitive types. So imagine every primitive type comes with a standard order. So for integers, for finite machine integers, just ascending standard order. Then we have constructions. Lexicographic order, that's on pair types. Okay. So first one determines, and only if they're equivalent, we look at the second component. Sum order on some types, which means like if you have some elements, you think of, you look at the tag first, and if the left one wins, okay? If it's a left element and the other one is a right element, then, the left elements come first. And amongst all the left elements, well, we use the, we need two arguments here. Like we use an existing left type ordering and a right type ordering, so that's the two arguments, they decide. They induce the order on the main type by a function and an order range type. I've mentioned that before, that's this map thing. Like, if I have a range of a function and there's an order on it, that induces an order on the domain. Okay. So if I, for example, we'll see an example to point that out. Okay. Recursion. So it turns out actually that anything that can be defined recursively also induces an order. So one has to be careful about the definition of order then in the end, make sure that this is a direct CPO, but it all turns out in the end to work. Inverse orders, well, inverse of an order is an order, right? So let's look at some examples. So first of all, to look at some examples, we have constructions, and that means we can define a term language for these constructions. Okay, let's do that. Here's the term language. So order of T means that these are order expressions over elements of type T. So what do we have? We have NAT, but this is only for the finite initial segment of NAT. So actually, well, even more finite than int is in Haskell. So for a given int, it defines an order on the initial segment from 0 to that int. Okay. So this is the argument here. That induces an order on all the integers. Okay. And definition of order makes sure that undefined elements can be in there. Triv just is our way of saying that's all the elements are related to each other at any type. Sum L is the one that I said before, it's the sum order. Pair L, that's the lexicographic pair order. Map O is the one that I mentioned here, is like for any order on T2 and a function, any function from T1 to T2, that induces an order on T1 and inverse. So that given any order, I get an order back. Okay, so examples. or char 8. Now imagine now I have nats 255. That means I have an order on the standard order from 0 to 255. Then I can apply the OR function from the 255. No, sorry. I can apply, sorry, on characters. I can apply the OR function on characters. That puts me into that domain. And that induces this canonical ordering on characters. Okay, so you can see this map-O in action. Map-O is also used for, actually, basically from this is just because we have explicitly, this is isorecursive, so we need to sometimes put this one in there. Otherwise, it's just basically for lists. It just means that, oh, it's the sum, which means like the left one comes first. So if it's the empty list, it wins. It's the left one. So that, it's just word unit, that's just true. And if it's the right, it's a pair. For the pair, then we say that's just the lexicographic pair ordering on the elements, that's the given here. And then recursively, we use the same ordering on the tail. All right. Okay. So, where are we? Okay. So, now we have terms. So can we get from these terms a function that we usually are used to actually using a comparison function? Well, that's easy, right? We do it by structural recursion. So if we want to have a generic less than equal function, which means that it takes an order specification and returns a function. And if we have LTE, we know that it will always be a comparison function. So even though it has this much bigger type, because this type is any function tt to bool, and in the range of LTE is only comparison functions, because you've applied it to something that's an order. So the structure of recursion is very simple. I mean, I've left out a test if you want to, but nat n x y, that just means like you take the primitive integer comparison. For triv is always true. For pairs, you can see here we do a recursion on the constructor pair L. It says, oh, okay, so lexicographic comparison, R1, R2. So we'll just compare R1, under R1, the first components, and if, and it's also has to be the case that this is less than equal, and if actually y1 is less than equal y, x1 is a convoluted way of saying they're equivalent, x1 and y1, okay, then we also have to check that LTE R2, X2, Y2 hold. Otherwise, it's less than, so it's definitely in a less than equal relation. Map 0, as I said before, all we do is like we apply the f function and then we compare under R. And the inverse is just as expected. You take x, y, and compare yx. So that's easy. So here's the idea. So let's think about the partitioning sorting function. So let's take sorting. We'd like to find sorting. We can't define sorting by comparison functions because, well, we can and it actually works in practice and it's still very nice, but we have a lower bound, right? So we want to actually exploit the intentional structure of our expressions. So by structural recursion, how do we do that? So using comparison functions, RT, L, R1, and R1, how do we construct comparison function for the product order? Well, that's how we did, okay? So we assumed that LTE is a function that we can call it on the component orders. Okay? Let's do the same thing for sorting functions. Or try it. So if you think about a sorting function having this type, takes a list of keys, so a list of keys, for the order, and we'll try to do this for pair L, sorry about that, pair L, R1, R2. Okay. So the idea is that we like to find a definition of sorting that has called sort R1 and sort R2, right? That's what we have. But that doesn't work because, well, in principle works, but it doesn't work efficiently, okay? Because sort R1 takes only the first components. So you have a list of pairs, and it only takes the first components and sorts them internally. But it loses the association with the second components. The same thing with the other one, right? So we need to somehow get a hold of the association. We need a more general functionality of sorting to make sure we can associate information with components. So we allow for what's called in the algorithms literature satellite data. be associated with keys. Okay, so that's kind of the other parts of a record than the key. So input key value pairs, sort the pairs according to order on the key components only, treat the value components parametrically, or obliviously is another term, which means like, let's just shuffle around, you never look inside of them, just think of them as like just having pointers to them, you never dereference. And drop the key component from output of sorting. Now I'll explain why that is useful, but basically the key is not going to be used anymore. So what we'll get is a functionality that, and the same thing here for partitioning, partition the pairs according to equivalence on key components, treat the value components parametrically, and drop the key components from output partitioning. So in a partitioning result, so which means that we get not only a list, but we get a list of lists, the functionality becomes key value pairs get turned into groups of values. Remember, we've thrown away the keys. And this is parametric, so the type actually in Haskell can express that. So for all the... Oh, okay. So this is actually the definition of a discriminator. So, discriminator equivalence relation E maps a list of key value pairs to a list of groups, where each group contains the value components that are associated with E equivalent keys in the input. So think of the keys now as labels. They identify what belongs together, but actually don't get returned. So, and it has to be parametric. So I'll skip this notation. This means that you know, don't look inside the values, which is good for algorithmic reasons. You know, this is like even if it's 50 gigabytes in the values, the only pointers that can get shuffled around. So it only depends on the size of the keys in the performance. So an ordered discriminator is basically the same thing. It's then a discriminator for the induced equivalence of an ordering, and the ordering induces an equivalence, right? Everything is less than equal in both directions. It's equivalence, and it must return the group of values in ascending order. That's all, right? That makes it an order discriminator. Okay, where are we? This is getting a little bit tricky. I mentioned this abstraction kind of thing, but I'll give you an idea. So we can strengthen the properties we require of a discriminator by saying, like, not only must it be parametric in the values, but if we have lists X and Y, so we have corresponding keys, and we replace a key by an equivalent key, okay, equivalent according to the original relation that we want to do a discrimination with, then the result should be the same. Remember, actually, the keys now get thrown away. So it really is to be literally the same result. That's what this means here. Okay? So discriminator if the output is the same for any kind of inputs where the keys are pairwise equivalent in this direction. One input is here, and the output is there, and then if they're pairwise equivalent, the keys here, then the output has to be the same. So, all right. So, if, for example, if a particular list representation does not play a role for a set when producing the output of a discriminator, when the list is a key. Okay. So our correspondence means I'll just give you an idea. So it means the discriminator is fully abstract. If furthermore it's the case that, you know, as I mentioned before, if the pairwise key equivalence is inside of one input, if they're the same as in the other input, then the result has to be the same. That's a stronger property. So I'll give you an example. So this is actually interesting when you don't only exchange a key at runtime or statically by another representation. Imagine you have an implementation where one list now gets, just for efficiency reasons, replaced by another one. That shouldn't make a difference in, you know, the application of a discriminator. But here it actually is important for actually pointer discrimination when you replace all the pointers and put in completely new pointers, okay? But pairwise occurring with the same identities, right? Then this property guarantees that you can garbage collect as much as you want, and the discriminator will always give the same result as it would have done before the garbage collection. So fully abstract implies partially abstract. You know, this is a proposition by a nomenclature. So let's look at an example. So we have, let's consider the equivalence relation. Think of it as like this. I want to represent booleans, but I used 32 bits. Stupid, but okay. sometimes not so stupid. So I use 32 bits, and it's only the parity I use to really, so, the even numbers represent true, let's say, 1 Boolean value, and the odd ones false. Let's assume that, right? So that's the equivalence we have in mind. So we'll do a discrimination of using a fully abstract equivalence discriminator. So we might get, as a result, this is a stable discriminator because it says, oh, here's a 5 and a 9. They both are odd. So they end up, their associated values, 100, 300, they end up in the same block. Okay? And they end up in the same order. So that's stable. That's just the same notion. It's a stable discriminator. So 4 is not odd, so it comes in its own group, 200. Okay? But notice actually, the 200 group, there's nothing in the definition says that couldn't come, the group here couldn't come before. Okay? That's an equivalence discriminator, if it were a, well, okay. So, by parametricity, discriminator, we can also from that conclude already that if we replace the 100 by foo and the 200 by bar and 300 by buzz, we know that the result must be this one, okay? Because D is not allowed to look inside of these values, so it just returns these values. That's the parametricity on the value part. Now, if it's also partially abstract, so by partial abstraction, it means like if I replace at any time any odd value by another odd value, well, the result still has to be the same. Okay? So think of this as saying like, there's one representation of false, by another representation of false. So please, the discriminator mustn't make a difference if I can use it safely. And it doesn't. And by full abstraction, it's interesting, we can even flip the meaning of true and false. So if we get tired of using odds for false and even for true, then as long as we take consistently here, like all the odds get replaced by evens, and the evens by odds, then notice that the pairwise equality is like it is not equivalent with any, but the only equivalence we have here is with 1 and 3. That's the same here. The only equivalence we have is between 16 and 4, right? Then full abstraction says, they're correspondent. The result must be the same. All these things can be implemented. So how do we do that? First, I'll show you as that a discriminator is like a great library routine. You can define, for example, sorted partitioning from it. It has a weird functionality, but all you need to do is like, if you really want to sort the keys and get the keys out of it, you just associate the key with itself. Okay? So the first component gets thrown away, and the second component gets never looked at, but it gets returned. That's just exactly what you want. Okay? So that does a classic partitioning, okay, in sorted order. Now, from that one, of course, we can just do sorting, namely just break up the partitions. Unique sorting can also be done, which means like return not all the elements, but only those elements that have no duplicate equivalent elements in the input. That's just we take the sorted partitioning, and then we take one element, let's say in this case the first element, in each one of those blocks. So sorted partitioning, that gives us blocks, and from each block, non-empty blocks always, and from each block we take the first element. And we've done unique sorting. Okay, so how to implement this efficiently, okay? All right, so we have, so we need, for basic order description, we just use bucket sorting. Bucket sorting is, so imagine now, in essence, we have recursively defined function at the end that has, and as you know, the leaf functions, these are all like multiple calls, the leaf functions determine all the performance in practice and in theory, okay? And the leaf function will be only 2, actually. Triv, which is really fast. Watch out, it's not trivial, actually. So in particular, you have to watch out, do not ever look in the key, okay, if you have only one element, because you don't need to. And the other one is all reduced to basic discrimination of short integers. So think of it as right now, for practical purposes, 16-bit machine integers. Everything else gets reduced to that case. So how do we do that? Well, you can use bucket sorting. Okay, there's all kinds of things, and there's variations that suggest that actually might use a combination of clever quicksort and various kinds of things in there. But the basic idea that I'd like to point out is the following: that you have a problem actually. We use a bucket table from 0 to n. We run through the input. Now the input consists of pairs where the keys are all 16-bit integers, okay? So all we do is we put the corresponding value inside of the table where the key says, okay? That's it. And then we run in ascending order through the index space. So this would be 65,536 indexes. And read out all the non-empty lists of values, okay? That's perfect. That's a stable basic discriminator, sorting discriminator. And this is the Haskell notation, if that helps you. That helps me more, I have to say. So, there's one problem here. It's like, if this gets called with like a list of 4 elements, okay, then there's 2 operations that are like humongously dominating everything else. Namely, allocate a bucket table and initialize it. This is like, whoa, like it's 65,000 elements. That's like, you don't, and then actually you run through the index space here. 65,000 things, you know, and you put in 4 elements. Now remember, there's potentially millions of calls to this function, and many of them will have very short inputs. That really hurts. So pair discrimination, I'll come back, but pair discrimination is the key thing that explains why we have discriminators. It says if you have a pair, then all we do is like discriminate on the first component. Now the functionality discriminator means that, oh, okay, we have reshuffled here. So we have the K1, K2 keys, and remember, you know, we always some kind of associated information. We reshuffle the inputs so that we associate K2 and whatever was associated beforehand with K1. Okay. Now, once we discriminate on K1, which means like group it according to K1, the K1 gets thrown away, and we get groups of K2V. Well, that's great. All we need to do now is discriminate on K2, and what do we get? Groups of V's. We're done. Okay. That's it. So that's the complete code. I don't want to take this usually. So here's the complete code for generic sorting discrimination. Okay. And this one is the bucket sorting. Everything I would argue is straightforward. Okay. So, all right. So examples, without going to it, you can do lexicographic sorting, but again, use desort if you want to sort according to these order relations and so on. You have to get used to actually writing your things down like this, but that's it. So the theorem is for each finite R, the function is to excuse the worst case linear time reduction on R, and then it gets a little tricky on the asymptotic time complexity for infinite R, which means infinite R are required for lists for non-finite data types, for trees, lists of all kinds. Okay. But basically, you can show that with some reasonable assumptions, there's a large class of these ordering expressions such that if you put them as an argument to S-discard, it generates a linear time algorithm. And as a corollary, you can look at the proof. As a corollary, it means that all standard orders on first order regular recursive types. So every type has, in a way, an induced standard order, right? So for products, it's like it's graphic order, some is graphic sum order, and for recursive ones as well, it's the recursively defined order. So they all of them give you a linear time sort of. I will skip this one and just gives you an idea of why when things yeah.
So you've got map in here. So are you assuming that the map function is constant time?
No. This is the tricky part, of course, because map always, if you want to look at the proof, this is where all the meat is and where the generality is. You have to use some properties. The basic idea is that, I'll give you an idea. It's like the map function has to have some properties, and it has to basically linear time in a strong sense. You can't possibly get a linear time algorithm with a very expensive function in there. So like, okay, but it has to be a linear and in this case, non-replicating. So it has to be linear really in the sense of linearity in type systems, in a strong sense. The idea is the following, is that you can't see it here, but if you wrote this for lists, which is like the sums, you would have a recursive call, right? So it's an amortization argument in the sense that the recursive calls, they get attributed parts of the input, the original input, to work on, or charge actually, and then the non-recursive calls, they must execute in linear time in the remaining size of their key space that is not hand it off to the recursive calls. Okay, but then you get basically a surprisingly tricky argument that says that it's linear type. I'm definitely not going to that one here, but we have to discuss it. So, all right, so we have this, we have that, and you know, the linear nonlinearity, and so in particular, it's interesting. Polymorphism, parental polymorphism, is basically a way of guaranteeing that you never look at parts of the input. So this is actually types. This is complexity by type systems. So basically, equivalence discrimination is now. This was for ordering. So let's look at equivalence for a brief time and try to. If we only want to actually partition and not sort, okay, then actually there's a good reason to do that. So it's like bucket sort, but we traverse the table in key insertion order when we read out the elements. So in other words, what we do is like whenever we put in a key value pair, we check, have you seen this key before? How can we do that? Oh, easy. We look in the table. Is the table empty in that place? Oh, then it's the first time we see this key. And we build up a key list of unique keys that we've seen. And once we're done with that, which is at the end, we run through the key list, which might be very short. 4. Read out from the array, and we're done. Ah, allocate. That's the last one. But allocation. Well, I don't know. You don't need to allocate. You just use one array. You just have a static global array. It's got to be empty in the start, and when you get out of it, it has to be empty again. Okay. So it's a global array we're using. So no dynamic bucket table allocation required. In particular, it runs asymptotically as fast as little as the inputs are. Okay. So this is the Haskell sort of prototype implementation. I believe this should be a systems routine. It's very important. It's not thread safe. It's not exception safe. It's not reentrant, non-reentrant in Haskell because of thunks. So you will notice the multiplication of here and here. So and I had to jiggle to get this past the type checker. Anyway. So but basically this is all basically a Haskell prototype, and it's important that it's this code. If you do functional arrays, not yours, John, which I think would be really lovely, standard functional arrays in Haskell, this will run 1,000 times slower, okay? And if you use actually even STMona or whatever, you run at least a factor of 10 slower, okay? So forget it, man. It's got to be this code. It's got to be this code you want to execute, really, at the bit level. So, but once you've encapsulated it, it's purely functional. Well, from the programmer's point of view. So the discriminator looks similar, and there's some tricky stuff going on here. I won't go into that one. That's the thing about, boy, that has to do with the permutation stuff. That's fun stuff. And but the results even hold with permutations and elimination of duplicates. So fully abstract. This is partially abstract for equivalence, non-containing bag E and set E. And if you want to have full abstraction, then there is a variant of this that is a little bit more expensive, and in terms of engineering, that's annoying. But it is fully, it's linear time for all the R's you've seen before, and it's fully abstract, and it's based on this. So let's look a little bit at performance to conclude here, okay? So this is a Haskell comparison with some standard routines in Haskell. Sort by is the Haskell library function. Qsort hand-coded with pivoting, of course. Merge sort, just straight top-down merge sort. SDisk and disk, okay? So this is for a so-called runtime minimum distinguishing prefix. That's the right input measure, really. It's only how many bits you really need to look at. None of them have to look at all the bits in this case. And it's for lists. So the input keys are lists of short lists of 16-bit numbers. And you can see that actually, I wouldn't overinterpret it, but I thought it was pleasant that in Haskell, I mean, the code we've seen here actually does quite well. So the discriminator is actually quite a bit faster for these cases here, okay? So this is even the SDisk, which has this problem of actually running up and down and allocating like maniac maniacally these tables is actually doing quite well. So for bags, this is actually quite tricky with the discriminator. Because this could be a bag of pointers. There's no order to exploit. You can, in particular, the standard way of doing it here is you take a bag, you just sort it first. And then you think of it as a list, because as lists they're unique. But what if you have no sort order? Okay. There's a way of doing this one by recognizing that we need to sort it, but the particular sort order is irrelevant as long as all the keys, all the bags making up the keys use the same sort order. Okay. So that's the key inside. So it's doing quite well. This is actually a classic mistake here. So if you do a pairwise comparison, by first sorting the element keys and then comparing them, that is really bad because you're doing a lot of extra sorting steps on the things. So if you do this beforehand, then you have the efficient versions here. So these are these ones, so it's better to see it here. So these are the three versions that you have to hand program. You first have to take the input, transform all the input lists by sorting all the input lists, making up keys, and then apply your sorting function. Okay. All right, so that is for medium-sized bags. So it's actually, I think, it's for something that just really is literally just very few lines of code. It's doing quite well. So yeah, this is for large bags, which means like the elements, there's a lot of elements per bag in the input. Okay, variation extensions not covered. Of course, was bucket count for sorting, domain theory, semantics, components questions, bag and set components discrimination, runtime order, and components normalization, which is actually fun because once you have these order expressions, you can, as opposed to actually just black box functions, you actually can rewrite them and say, like, oh, that one's equivalent to that one. I know this one is actually going to be better for my algorithm. I'm going to rewrite. So I'm normalizing it. I'm doing algebra. I can do it at runtime. So application data storing discriminator joins. I haven't shown you that, unfortunately. There's a couple of works that this looks like a rather exciting application area for it. And the combinatoric discriminator library, which requires rank tupolomorphic types to avoid the GADTs. Accuracy is not quite as efficient in Haskell as the GADT code I've just shown. And the comparison of complexity of sorting, many things about sorting are like digital merge sort runs in quadratic time in the worst case. So, contributions. As a number, I think, I hope you've seen it's possible. So the bottom line is the following one. If you design an abstract data type, and it should have an equality, right? Give it to the world by having the equality observed by a discriminator. Don't give it to them by a pairwise comparison function. That one is basically semantically sufficient, but algorithmically completely insufficient. And get rid of num_by, for example, then. Okay. So, and the same thing, of course, with sorting. Okay, that's not so important. N-log-n isn't that bad in practice. It's like, don't give it as a pairwise comparison operation when you design a new data type to observe less than equal, but give that observation as a discriminator. Notice it's simple exercise. Having a discriminator, it's trivial. Just apply the two arguments list to get a comparison function out of it. Okay? But we need the discriminator to get fully abstract still. You're not doing hashing and all of a sudden numbers observing abstract data types. You get basically all the semantic abstraction, the full abstraction, data abstraction, and you get full performance, best possible performance for these kinds of partitioning and sorting that happen. So, there's discussion of future work. I'm out of time. So, there's all kinds of things, and I'd like to invite you to actually work with this and play with this. Unfortunately, it's not on package for the simple reason that I have a hard time putting code up there I know is not right, like the basic discriminator. It's not thread safe. But everybody's welcome to contact me, and I'll be happy to give you the code. And maybe some of you can even figure out how to get it past the Haskell type checker. So, so there's a number of works. Actually, it started in the algorithms community, basic multi-set discrimination. Then I got interested in that one, and we applied it in a peer-to-peer basis in the store and developed some of the techniques in it. So we have also Java discriminator library. 2008, I basically presented the basics of it, and actually a much delayed paper. Yesterday I got to know that it's not coming out in July. in November is where you can read about this one, JFP. Until then, you have a great opportunity to look at basically the same paper on my homepage, okay? So no subscription of JFP is required. So be sure to join us applications. There's a number of applications, and if you want to hear them, there's actually one of them at ICFP. So I hope actually to see you at ICFP, as many of you as possible in Copenhagen in a couple of weeks. Thank you very much.
Yeah, thanks for a great talk. I think we have time for questions.
Your order T-type is not very extensive. You can add.
Yeah, okay, yes. It's not, right now it's formulated as a GABT. You have to add to the GABT, yes. So you can make it open, right? So various tricks you can embed the whole thing into, the class, Haskell's class system. Yes. So basically, phantom types. Oh, okay. They're not data types. Yes. They're not regular data types. Yes. So the GABTs play a major role there. Basically, it's a small language for defining constructions. And you could make it open because the whole approach here is that you have to define a clause, a recursive clause for each construction. Right? So for each construction, if you define sdisk or disk or whatever, you have to just say, oh, okay, there's a new constructor. Then I just have to design do it generically. I can say a lot more about that. So yes.
I have another question as well, complexity. I saw your implementation of reverse and concat map because you use prevention and everything. How do you get in there? Also in the comparison of quicksort, it's not your quicksort. Quicksort Haskell uses concatenation as well. Usually you split quicksort to be done on arrays.
Well,
to traverse lists
yes,
when you operate on them.
The concats here actually don't hurt. They're the ones you've seen. These are not like iterated concats. No, actually it doesn't, because it's only used. It's not used iteratively. It's only used sort of once on the output. I mean, in practice you wouldn't do that. So the reversal, I have a whole workout, the whole thing with reverse stable once, just to avoid all the reversal here, right? And the properties work out, and it's just more complicated to present. But it does not change the asymptotics. So these reversals are harmless, let's say, in terms of asymptotics, but in practice they hurt. So there's this flip-flop thing, that's where the reversal really hurts, because you really reverse something and then you reverse a subpart of it again, and reverse that again and again, so you get quadratic time that way.
So, linear time is great, but we're limited to 16-bit numbers. And if I go to 32-bit numbers, obviously my bucket's going to get huge. So in practice, right, if I replace that bucket, at the leaf there with a balanced binary tree, kind of system, I know I'm going to lose the asymptotics. But in practice,
actually there's a little trick here. So what did I have this? Anybody remember? Okay, here's the trick. Net n, this can be 32-bit number.
right?
So x, this is any number. So if it's below 65,136, we do actually 16-bit. If it's not, we do a recursive call this EQ is 32. What does that do? It basically treats every 32-bit number as a pair of 16-bit numbers. And we already have the code for 16-bit numbers. They just do the discrimination on that one. So what that means is that you're running through the input twice. But that's it. And you're still only using a single 65K bucket table.
Is that the right layout? Yeah. Using an 8-bit table.
You could play with that, yes. But you can play with that. The 8-bit table makes the
4 times.
Yes, yes. But for this actually doesn't make a difference, because the technique is that as long as you space for that static table, there's no cost in traversing it, assuming random access hypotheses. There's no cost in accessing because you only really use as much time as what the actual number of elements you put into it.
What about 2?
What about 2? Sorry, 2 elements. Yeah. So you get 2 elements. If they're 2 different keys, then you get you put it in 1 there. You have a key list of length 2. You look at the key list and say, "Oh, give me that one out again. Give me another one." You're done. And 1 is great. You never put it in there. You just say, "I'm done." Yeah.
So we're thinking about bucket sizes, and you presented MapO, which was using something like 2 upper to change the charge of the upper only. That shrinks the domain, the range. Do you have any clever tricks that make that faster as well, or that mean that we're using fewer buckets?
You're talking about this here, or?
So I'm thinking about you had MapO 2 upper on add char or on something char A or char A, I think it was.
Ah, okay.
So yeah, that example. So the 2 upper is going to shrink it so that you have fewer chars to worry about now, half of them, because you're only considering the uppercase ones. Do you do something with the buckets there as well?
No,
is it possible?
no, absolutely not. There's all kinds of tricks you can play conceivably. One of the things, so no, not here. So this is still complete naive in that sense, and there's some results in radix sorting that indicate actually you can get some very space efficient implementations from exploiting the information theoretic properties of sorting. Maybe, if you have a sorted output, knowing that they're sorted actually means that it takes less space to store such a list. Okay, and you can play all kinds of tricks, but that's not done here at all.
Okay, and one last question.
So I was wondering about the domain-specific language for ordering. So do you plan to extend it? What sort of simplifications are you making? I mean, you had an inv at some point, so if you invert an order twice, can you eliminate that?
Yes. There's an algebra that's actually described in the paper too. Okay. So you can do the following. It's convenient to just have an order. Somebody has an order in there, and then you just say, I want the inverse of your order, right? And whichever order it is. Now it happens to be that in your implementation you used in, right? Then there's a rewriting step possible that eliminates that one before actually doing it with the actual discrimination step. So there's a couple of simplifications that make sense. I mean, they're basically extensionally both, algebraic equalities, but one of them has fewer calls to S disk or disk.
Okay, thanks again.